Okay. Yeah. Today's discussion will going to be about machine-dependent assembler features. That is, those features which are specific to SICXC, which is not covered in the algorithm of SIC machine. So these are some of the additional features what we're going to see. And also we have machine-independent assembler features also. Those are not specific to the architecture of the machine, but they are the desirable features that gives additional power to your assembler implementation. So those things we're going to discuss in the next chapter, right? Yeah. SICXC supports different addressing modes, specifically with our format 3 instructions such as PC relative, base relative, immediate, and indirect. How to assemble the program with this particular thing is what is the discussion today. Yeah. So based on the assemblers, different addressing modes, we're going to have the different what you call designs needed in your assembler. The first format 1 instruction don't contain the operands, so there is no addressing mode, so there is no specific assembly rules for them. But the format 2 is a register to register addressing mode, which we discussed actually, but I got many of the requests that the slides were not visible. So we shall see today. Yeah, format 2 instruction is having 8-bit opcode followed by 4-bit and 4-bit registers, right? 4 bits is used to represent the registers because we have 9 registers. We cannot represent them with 3 bits. 3 bits can represent only up to 8 registers, but as we have 9 registers, we are supposed to go for 4 bits. So 2 to the power of 4 gives us 16. So for that reason, we are using 4 bits. But anyway, we are only supposed to represent 9 registers. That's it. Yeah, we shall see the assembly of one such register to register addressing mode. Here we have add R, which is the addition operation with register to register. We are telling to add the contents of S register with the contents of T register, right? So the add R, the opcode is 90, which is written as 1001 and followed by the zeros, right? And 8 bits. And followed by the S register, which is given 4, value 4, and the T register, which is given the value 5. These are the register numbers what we use when we discussed about the architecture of SICXC, right? And then an example one more, wherein we have COMPR instruction, and COMPR A0 is the opcode, and X register is 1 and A register is 0. So A is represented as 1010 followed by 4 zeros, and 4-bit registers. Register X is represented as 001 and the accumulator is represented as zeros. Fine. One more example is the TIXR, so which is B8 and 14. Right, B8 is represented as B is represented as 1001011 and 1 is represented as usual. That is suppose 8 is represented as 1 followed by 3 zeros, and the accumulator is the one that is being compared with S register. So the first register is accumulator, so which is zeros followed by register S, which is 4. Represented as 0, 1, 0, 0. Fine. Okay, this is about simple assembling. There's no much variations. Register to registers, 2 registers using 4 bits and 8-bit output. But the challenging things are PC relative and base relative addressing. We shall have a look at those particular things. PC relative, most of the instructions what we write in our SICXC program will going to be of format 3 instructions. That too, majority of them will be PC relative. I kept on repeating these things again and again until unless the base and no base assembler directives are not used, the format 3 instructions is supposed to be assembled using PC relative addressing. So that's what we are trying to do now. Fine. Okay. Target address is calculated by adding the contents of PC with a displacement, and displacement is computed by subtracting the target address, subtracting the PC value from your target address. So that's that calculations we have seen. Right, now we shall see how the assembling will happen. right? And try to understand one thing. If a PC relative is a forward referencing, means the declared value appears after the instruction, you will going to get the displacement positive displacement, because you are in fifth instruction. PC will be holding the address of sixth instruction, but the target address will going to be somewhere at 10th or 11th instruction. So 6 minus 12, you're going to get the 6 displacement. Obviously, I'm just telling you a simple math. So it will be a positive displacement. But if the displacement means if the reference is appearing before, which usually will happen due to your backward jump, something like to a label. If that sort of thing happens, then the displacement will going to be negative. Because suppose let me think I am at the 12th instruction, 11th instruction, let me think. PC is pointing to your 12th instruction, and you are supposed to go back, jump left then, or jump if greater than, to a fifth instruction. Then obviously you are going to get a minus displacement or negative displacement. Right? That's what is the difference. What is going to happen? We shall see. Yeah, and usually the B flag will be 0 and the P flag will be 1. So the displacement can range from minus 2048 to plus 2048. With this range is what is possible with the displacement. Okay, let's see an example. We have a instruction at 6, which is LDL return address. Okay, load L register with return address. So return address is being declared at 0036, which is a integer variable. Okay, so how shall we assemble this thing? You can have a look at this. Target address is equal to PC plus displacement. Displacement is equal to target address minus PC contents. So 0036. When your instruction is at 0006, obviously the next instruction would be in 0009 as usual. So 36 minus 9, 0027 is what is the displacement you are getting, which is actually a positive displacement. 36 is appearing after 0009. So the displacement yields to be 0027. How to assemble? Please observe this. This is actually you will not be given a code of SIC machine to assemble it. But if at all it is given, it will be a SIC XC. So the possible question from the machine dependent assembler features will going to be giving a code and asking you to convert it into an object code. So wherein you should be careful about the flags, careful about the computation of displacement and all of this. Please observe now. Actually, we have I have discussed about this when we discussed about the architecture. 1 or 2 examples we have seen there. Now in specific, we shall see a implementation of this. Okay. So LDL opcode is 08, but here one more issue arises with the format 3 instructions. What is that is, we will have the opcode not of 8 bits, but only of 6 bits. We am repeating, in format 3 instructions, we'll have the opcode not of 8 bits, but will going to be of 6 bits. So for that reason, the last 2 digits of your opcode should be truncated. Yeah, last 2 bits of your opcode is supposed to be truncated. Observe the example, you can understand. The opcode of LDL is 08. So this is what we have got. What is that? 0 is represented as 00004 bits, and 8 is represented as 10. Actually, 8 will going to be 1 followed by 3 zeros, but we are representing it as just a 10. You cannot read it as 10 as 2, but it is 8. 10 is 8. Why? Because the rest of the bits is used for your flag bits. And as it is a PC relative addressing mode, N and I bits is 1 and 1 as usual. X is not an indexed addressing mode. So, and the indexed is not possible with PC relative. Remember that index can be possible only with base relative addressing, right? So X bit is 0 because it is not an indexed addressing mode. P is 1 because it's a PC relative. E is 0 because it's a format 3 instruction. And now the displacement. What is the displacement? 0, 0, 2, 7. That is represented as 0. We have 12-bit displacement. So we cannot represent 0, 0, 2, 7. So we are representing 0, 2, 7. That's the displacement. So first 4 bits is zeros. Next 4 bit is representing 2. Next 4 bits is representing 7. 0, 111 is a 7. So now how to generate the object code for this? This much we have seen in the architecture, but how to generate the object code for this? We can generate the object code by grouping the 4 bits together. So after writing this, we'll group the 4 bits from the most significant bit towards the least significant bit. Whatever the resultant hexadecimal values we get, that will be our what you call object code. How is it? Just have a look. We have grouped the first 4 bits, which is giving me 0. First 4 zeros, so it is giving me 0, followed by next 4 bits is grouped, that is 1, 0. 1 is grouped, which is giving me B, right? And then the next 4 bits is grouped, so it is giving me 2, 0, 0, 1, 0. It is giving me 2, and the next 4 bits is giving me 0. Next 4 bits is giving me 2, 0, 0, 1, 0 is giving me 2, and the next 4 bits is giving me 7. So the entire opcode for this instruction, LDL return address, will going to be 0B2027 hexa, right? 0B2027 hexa. This is going to be our object code for assembling of PC relative addressing, right? So this way we are supposed to group the bits and find the object code when it is a PC relative addressing. Be careful. This is you can expect one such question in your examination, because this is the flag combinations as well as the computation of displacement. All these things should be done. First compute the displacement, then find the opcode, write the opcode in 6 bits, and then set the flags accordingly, and then compute the what you call object code by grouping 4 bits together. Fine. So this is one of the example. Yeah, we shall see one more example of the PC relative itself. Yeah, here we have C loop, which is at the location 0006. Actually, I am supposed to write it towards the left hand side because it's a label. It's not a what you call operand. It's a label. We are supposed to write it on the left hand side, but no issues. And the target address is 0017. Now we are supposed to jump to C loop from the instruction which is at the location 0017. When the address is at 0017, the PC value obviously will going to be the next instruction, that is 001A. From 001A, we are supposed to jump backwards. Means it is a backward jump. It's not a forward jump. The earlier example, the declaration was of the return address was later, so it's a forward jump. But now it is a backward jump. So earlier you got positive displacement. Now you are supposed to get a negative displacement. Please try to understand. Yeah. So as usual, target address is equal to PC plus displacement. Now the displacement is supposed to be calculated by subtracting the PC from target address. So 0006 is our target address minus 001A, which is our current PC value, the current PC value of which instruction? The instruction at 0017, right? So we got the displacement as FFEC, which is a negative value. FFEC is a negative value. We are supposed to jump back, and all calculations are hexadecimal calculations. Please remember, and you are supposed to use your calculators in hexadecimal mode so as to do the subtraction. Please don't do the decimal calculations. Please don't do the decimal calculations, or else you'll end up in a wrong displacement values. So that you should be careful about. Fine. Now the FFEC is the displacement, but I cannot accommodate FFEC in 12 bits because I have the space for writing the displacement is only 12 bits. But here I need 16 bits for writing. First F 4 bits, next F 4 bits, next E 4 bits, and C 4 bits. That's not possible. So what we will write is, instead of FFEC, we'll write FEC by eliminating or truncating the first F in my displacement. Right? We will be truncating the first F. Right? And LDL opcode is 3C. 3C hexa. So 3C is 3 is 0011 and C is 1100. Now we are supposed to truncate 2 bits of your opcode. So we'll be truncating the last 2 zeros. So what is the opcode we'll get is 0011 followed by 11. Fine. And rest of the things will going to be your flags. Okay. So this is how the things is written. First 3 is written as 0011 and C is written by 11. That's it. And N and I flag is 1 and 1, X is 0, B is 0, P is 1 and E is 0. Now FEC is written in the place of displacement. You can see F is all 4 bits of 1s, E is 1110 and C is 1100. Okay, let's group the bits together and find the object code. So this first 4 bits group will give you 3. The next 4 bits group will give you 4 ones. Will going to be 4 1 is nothing but your 50, which is given as F 3F, and 0010 you're going to get a 2, and 4 bits together again an F, and then an E, and then a C. Okay, so this is our object code computation for the next PC relative addressing. So I have taken one example, which is a forward jump, and one example of a backward jump. Usually, backward jump, it's specifically the backward jumps displacement will going to be negative displacement, and forward jump displacement will going to be a positive displacement. Okay, so JC loop. Now the object code will going to be 3F 2FEC hexa. But last H is your hexa. Okay. Yeah. Let's move on and see the base relative addressing mode. How the assembling will happen, very similar to this, but we shall specifically see that. We know that the target address is calculated by adding the contents of B register with the displacement. For calculating the displacement, the reverse process is used. B flag is 1, P flag is 0, and indexing is possible with base relative addressing. Okay. The displacement can range from, now the range is increased, is not minus 2048 to plus 2048, but now it is starting from zeros to 4095. If you can make an estimate of why this is so, because usually the displacement value will be first. The same logic with the 2's complement will apply. With PC relative, there is a possibility of positive displacement and negative displacement, because you can jump forward and jump backward, usually used with jump instructions and other things. But the base relative is usually used with array operations. So array operations will be going to the next element and next element and next element and next element. So that's the specific use of our base relative addressing. Usually the index, that is the index of the array, will be stored in your X register, which will be kept on incrementing. That's the reason why we have TIX and TIXR instructions. TIX and TIXR instructions allows us to compare the X value. X will be incremented and then it will be compared with the count. That's the reason of TIX and TIXR instructions. So increment the index value, then compare it with the the count value. If it is if it is less than, we'll be keep on going to the next element and next element and next element. So specifically to work with the array operations, we're going to use indexed addressing mode. That's the reason we use indexing can be used with base register, but can be used with base relative, but cannot be used with PC relative. This is one sort of rule you can make, that wherever you want indexing should happen, you can go for a base relative addressing mode. That is not possible with PC. And why PC relative is used? Specifically to address the locations either forward or backward. That's it. So simple arithmetic and jump instructions can use your what you call PC relative. That's also usually will happen. Okay. Yeah. And the contents of the B should be specified prior. And as we know that base and no base assembler directives should be used. If it is used, then the instruction between this base and no base should be assembled using what you call base relative. Else, all the format 3 instructions will be assembled using PC relative. Have a look at the example. So we have at 0003 an instruction LDB length. LDB load the B register with the length, and then length is a variable, means that will come next. Okay, and base length, I am specifying base assembler directive, which should use the value specified in length, right? Okay, and between base and no base, we have an instruction add alpha, which means contents of accumulator should be added with alpha, and the result should be stored in accumulator. And after that, we have a no base assembler directive is telling that further after this, any format 3 instruction comes, that should be assembled using PC relative. And before 6, means 0006, the instruction is supposed to be executed using PC relative, right? That means LDB length will be assembled using PC relative. Only the instruction add alpha will be assembled using base relative. Is it fine? Okay. Yeah. And len is being declared in 0033, which is a word. Word means an integer constant, whose value right now is 3. Fine. Okay then. And alpha is a integer variable, which is declared in 0036. Means now load B register with len. B register will be containing the value 3, right? Fine. Then, so as usual, target address is equal to contents of base plus displacement. Now the reverse of it, which you can see, displacement is target address minus base register contents. Okay. So 0036 is where alpha is, and minus the contents of B register, that is 0003. So we are going to get the displacement 0033, which is a positive displacement. Okay, and our code for add is 18 hexa. Now again, 1 is represented as 00001 and 8 is represented as 10, right? Because 8 is 1 followed by 3 zeros. You're going to be truncating the last 2 zeros, right? This is what is the implementation. So our code is written 1H followed by N and I flags are 1 and 1, X is 0 because there is no indexing is used, but we can use indexing with a base register. We shall see that also. And P is 0 now because it's not a BC relative, and E is 0 because it's a format P instruction. And the displacement is 033. So mentioned as 4 zeros followed by 0011 and again a 0011. We shall group the bits now. Again, the same set of same type of grouping as we did with PC relative should be done here also. When I group the first 4 bits, I have got a 1. When we group the next 4 bits, that is 1011, we got a B. And when we group the next 4 bits, I got a 4. And then next 4 bits, we're going to give you 0. Next 4 bits, we're going to give you 3. The last 4 bits, you'll get again a 3. So the object code for your add alpha is 1B4033 hexa. So this is how the assembling is done for the base relative addressing. Be careful, it is a base relative addressing mode. We should find the displacement by subtracting the contents of B register from the target address. And you should be capable of specifically locating which instruction is a base relative. Any instructions that is appearing between base and no base or base relative addressing. If the base and no base is not specified, then by default the format 3 instruction will be considered as PC relative. In our example, the instruction at 0003, that is LDB len, is a PC relative addressing mode, and add instruction at 0009, add alpha, is a base relative addressing mode. Fine. We shall see one more example. Yeah. Here we have one more example. Same thing. LDX immediate with 1 and LDB what do you call len, base len. It's assembly directive being used. And then we have STCH buffer comma X. So between 6 and 12, the instruction at 9 is a base relative addressing because it is appearing between the assembler directive base and no base, as well as it is an indexed addressing mode because beside the operand you have the X is been specified. Okay. Length is an integer constant of 3 and buffer is declared in 0036, which is a array of 100 integers because we have used RESW, reserve word 100. Fine. Okay. Then target address is equal to is computed by B plus displacement. Displacement is equal to target address minus B minus X. Both should be done because it is now a base relative with indexed addressing mode. So target address is 0036 minus 0003, that is the contents of your B register, minus X. And as you can see in the first instruction, we have loaded X with immediately with a value 1. So 0036 minus 0003 minus 0001 is going to give you 36 minus 4, that is 0032. This is what is the displacement you got. Fine. And we have STCH, which is 5 and 4 opcode, right? So now we represent the opcode in 6 bits. So 5 is completely represented 0 1 0 1, and 4 is represented only 2 bits, that is 1 0. So this is 6 bits opcode. N and I flag are 1. Now X flag is 1 because it is an indexed addressing mode, and the B flag is also 1 because it is base relative addressing mode. P is equal to 0 and E is equal to 0. As usual, our displacement is represented here. We can only represent 032, not 0032, 032. So 0 is represented 4 zeros and 3 is represented 0011 and 2 is represented 0010. Now let's group the bits. First 4 bits gives me 5. The next 4 bits gives me B, right? Next 4 bits gives me B. And usually you can see the second bit will going to be either B or F, like that, depending on, or else 2. The reason is, if the first 2 bits is 0 0, it is going to be 3. If first 2 bits are 1 and 1, it is going to be what do you call F. If the first bit is 0 and the next bit is 1, it is going to be 7. And the first bit is 1 and second bit is 0, it is going to be. So only 4 possibilities, right? Either 2 or either 15 or either B or either it is 3. These are the 4 possibilities that is possible for your second 4 bits, right? And the next bits, next 4 bits when we group, we're going to get a C, 1100, and then we get 0, 3, 2 for rest of the bits. So the object code will going to be 5BC032 hexa, right? So this is the way the PC relative and base relative addressing mode need to be what we call assembled, and we have a program example also for the that also we're going to see the program example. Fine. And next we'll go for an immediate addressing mode. This is very simple. LDA 9. LDA instruction is 00, right? So 0 zeros is represented in 6 bits. We got 4 zeros followed by 2 zeros. So when we as it is an immediate addressing mode, I is 1, N is 0, X, B, P, E, all of them are zeros because it is not a PC relative, it is an immediate addressing. So first 4 bits when I group, I got 0. Next 4 bits, I didn't told about this because the immediate is different. We spoke just about our PC relative and base relative, which is only 4 values that are positive, right? And next 4 bits when it is grouped, it is 1. Next 4 bits when I group, I get a 0, then a 0, then a 0, then a 9. So the object code is going to be 0, 1, 000, 9 hexa, right? So this is how about assembling these 3 different addressing modes: PC relative, base relative, as well as immediate addressing. Usually we don't use indirect addressing, so that's why we don't have a particular part, right? So we are one more example, LDX4. So 04 is the thing. So we have used 1 followed by another 1 followed by 0 followed by 0, 0 and a 4, right? So 11, 000, 4 hexa. This is what is the object code for your immediate addressing, right? So these 3 addressing modes we learned today: PC relative, base relative, as well as immediate. How to assemble it, right? We'll continue in the next class with much more features, and we'll see a program and an example also. So thank you for joining. Fine.